Right. So Shandeep, the recording has started. You can.
Okay, good. So, hello, folks. A very good morning to all of you. So, welcome back to this webinar series from ACM Mobile. So, for the students or the participants who are new to this webinar, let me quickly introduce about ACM Mobile. So, ACM Mobile is the India chapter of ACM Mobile, which officially started in March 2019, just before this COVID pandemic started. So we have our own website and the social media pages. So I think that many of you are already subscribed there. If not, please subscribe, that you will get the regular updates from ACM Mobile. So the broad objective of iMobile was to boost up the system research in India, particularly the research in the areas of mobile computing, sensing, almost all the areas that are being covered by SigMobile, and to have a strong presence of ACM SigMobile in India to make a collaborative platform among all the people who are doing research in the areas of mobile computing. So with that objective, we have started this ACM Mobile in 2019, and we had our first workshop along with ComsNets in 2020. But after that, the pandemic hits, and we are just holding up our all our events, particularly these webinars online. And hopefully soon we are going to back to our normal in-person activities. So this is the team for 2022 for ACM Mobile. So we have Amit Saha from Cisco as the iMobile chair. I am Shandeep Chakraborty from IIT Kharagpur. I'm the vice chair of ACM Mobile. Jagadisha from IIT Dharwad is the treasurer. Sogato, who is soon going to introduce you with Ranjita. So Sogato is the event coordinator. We have Rohit from Intel India as the web chairs, and our mentors, Venkat from Microsoft Research, Suman from University of Wisconsin-Madison, and Rajiv from TCS now at IIT Delhi. They are our mentors. So that's pretty much about iMobile. So just before I end, I would encourage all of you to join ACM SigMobile and in terms ACM iMobile if you are not a member of ACM iMobile yet. So the joining process is very simple. You can just join SigMobile, and by default you will be able to be a member of ACM iMobile. And for joining SigMobile, the annual membership fee is very less. It is around $25 for ACM members, around $30 for the non-ACM members. And for students, it is only $5. That means something close to 400 Indian currency. So I would encourage all the students, all the others who are here to join SigMobile and ACM iMobile to grow up the community. So you can find out the joining procedure in ACM iMobile website. As I mentioned that it is just about you join as a SigMobile and mention your location as India. By default, you are going to be a member of ACM iMobile. And if you see that ACM iMobile has not been listed in your membership, just follow this procedure which is listed here. So that's all. Without not wasting much time of you, let's move to our webinar. So Shogato, over to you.
Yeah. Thank you, Shandeep, and good morning, everyone. Welcome to the webinar, and it's a pleasure to have Dr. Ranjita as our speaker today. And thank you, Dr. Ranjita, for agreeing to participate in this webinar. So just a brief introduction. I believe a lot of you already know Dr. Ranjita's work, but Dr. Ranjita is a senior principal researcher at MSR India. She has worked for more than a decade on applying machine learning to improve system reliability, security, and performance. She has focused on data-driven approaches to improve cloud services, and she's an active researcher who is publishing at top-tier conferences. And indeed, her work won the Best Paper Award at Usenix OSDI 2018. She is an ACM Distinguished Member and is the recipient of the ACM India Outstanding Contribution to Computing by a Women Award. Dr. Ranjita has chaired multiple top-tier conferences in the field of systems and networking, and is on several conference steering committees. She has received her PhD and MS from UC San Diego and her BTech from IIT Kharagpur. So, without further ado, it's a pleasure to welcome Dr. Ranjita, and over to you.
Thank you, Shogato and Shondeep also for inviting me and for that great introduction. I will be speaking about how over the last 3 years or so, we have been working in the area of cross-layer optimization in Microsoft, given that Microsoft is a large cloud provider. So I will be talking about this. And feel free to raise your hands, ask questions by unmuting, because I think it's a fairly small audience, so we can keep this interactive. And I will make sure that I use my time properly and end on time. But let's keep it interactive. If you have any questions, doubts about what I'm saying, if something is not clear, please feel free to clarify. All right. This is, of course, joint work with a large number of people. So at Microsoft Research in India, we have a lot of great research fellows who come and work with us after their bachelor's or their master's for about 2 years, and they get a flavor of what research really is. And then if they like it, they can go ahead to PhD programs all around the world and in India. To do their PhDs. So Sagar, Praveen, Harsha, Parth are research fellows who have worked with me in the past. And this is joint work with Venkat Padmanabhan, my colleague, and also with various folks in our engineering teams in Microsoft 365, what you might know as Office 365, and also the Azure network. Folks, and these folks are spread across Redmond and Suzhou in China. Okay, with that introduction, let me just give a high-level overview of this project that we are working on. Microsoft, Amazon, Google, these are all companies that run really large clouds these days, right? So because they are running these clouds, they have a huge amount of access to information at various levels. So for instance, you have user information. For instance, when the user logs in, or their calendar information. You also have application level information. So what does the application behavior look like? Is there any deadline associated with the traffic that this application sends? What is the metadata it generates, etc. Then you also have infrastructure level information. For instance, how much compute capacity there is in every data center, what is the cost, how many failures happen in the data center or the network, what is the nature of these failures. So in general, there's a lot of data available for each of these layers. So what we can do then at a large cloud company like Microsoft, which has all this access, is that we can take all this data, which we call telemetry, then you can build models for each of these layers separately. So you can build a user model, you can build an application model, you can build an infrastructure model, and then put this together to do cross-layer optimization. So for instance, the user model can be used to do better efficient allocation or resource management at the infrastructure level. Or infrastructure level information can be fed back to an application so that it can be more resource aware in its decisions. So I'm going to be talking about two specific concrete problems that we have worked on in this area. So I'll be spending most of my time on the first one, which is about optimizing network provisioning using this cooperation between application and infrastructure. And then if I have time, I will talk about using application level queries to discover related data, which is more in terms of how do we manage telemetry, how do we build these models. All right. So I don't know if I will be able to see if people raise a hand. So Shogato, I'll depend on you to please interrupt me if there are any questions.
Sure, I will do that. And so to the audience, if you don't want to raise your hand, you can put your questions in the Q&A as well. We can take that.
Great. it. Thank you. Okay, so the first piece first work that I'll talk about is about optimizing network provisioning through cooperation. This is work that we are actively doing with the Azure networking folks and Office 365 folks, but a paper on this has also appeared at NSDI in 2022. Okay, the Microsoft WAN is a beast. And for any cloud provider, the WAN in general is a quite large beast, where you have these data centers in different locations around the world. The dots are data centers, and or even edges, and then you have links which connect these points of presence across oceans, across large continents, etc. So as you can understand that building such a big WAN takes a lot of resources in terms of time, money, effort, etc. Right? Now, when before I talk about the specific problem we are targeting, which is network provisioning, let me first say what network provisioning is not. Network provisioning is not traffic engineering. Traffic engineering, which is a field that has seen a lot of attention in the last few years, is the following, right? Given a network topology, given that there are links of certain capacities in the network, how do I route my traffic for best performance, for fairness, for availability, etc.? This is the problem of traffic engineering. Network provisioning is the problem that targets the first part of that sentence I said. Traffic engineering assumes that the network is given. Network provisioning is about building that network. So, let me say now, what is network provisioning? Network provisioning first forecasts demand from the applications. So it observes the history of network usage by applications and says 6 months from now or 3 months from now, this is the amount of traffic this application will generate from, say, a data center in Singapore to a data center in Hong Kong. So this is the first step for network provisioning, which is forecasting of demand. Now, most forecasting techniques, most network provisioning techniques, state of the art, use peak provisioning. So you will forecast the demand, which is the squiggly curve, and then you will take the peak of that and say, this is the amount of capacity that I need to provision for, because you have to provision for the worst case, for any resource for that matter. Okay. The next input to network provisioning is a topology of the network, and I'm talking about the physical level topology here. So you know that there is a fiber optic cable going from, say, New York to London. So this information has to be input to the network provisioning algorithm. The output from the network provisioning algorithm is essentially this network, which is the shape of which is given. But the network provisioning says how much capacity we will need from data center 1 to data center 2. And so that's the input, sorry. And the output says for every link in my network, which I know, what is the capacity I have to provision for. So in this small example on the right of your screen, it's saying that data center 1 is connected to data center 2 with 3 links, and I'm simplifying. Actually, there will be multiple links connecting them, and there will be routers in between, but I'm simplifying with just a single link, and I'm saying that there are 3 links for redundancy. Two have 100 Gbps of capacity, and the third has 200 Gbps of capacity. So you can imagine extrapolating this whole process for the whole network. So this is the problem of network provisioning. Okay, now to actually do this network provisioning, there are 2 things that the network provisioning box here needs. One is a network failure simulator. So the simulator says that if a link goes down, it simulates a failure of the link so that you know how much redundant capacity to provision on other links. Right? The traffic engineering simulator determines or is a building block, because you need to know the routing strategy to figure out what links to put capacity on. I see there is a Chat. Okay, wait, no, it's nothing to do. Okay, Ashogata, I'll depend on you to curate whatever comes.
Yes, sure, I will do that.
Okay, thanks. All right. So now let me say how network provisioning is done today. And when I say is done, I mean in companies like Microsoft, and also in the very few research papers that talk about this problem before ours. The application level is separated very nicely from the network right now, and the API is very simple. The network operators, they observe the application's usage of the network and they provision based on that. They just notice, okay, the squiggly line is how this application used the network from, say, data center 1 to data center 2. That for the future, and that's what I will use, right? It's a very simple technique. But our observation is that when the application and the network are both owned by the same entity, in our case Microsoft, you can do a lot more. You can make the interface porous. Okay, so if the application tells the network that some characteristic about its traffic. So in this example, I'm saying the application tells the network this brown line, or if it looks red for you, reddish brown line is the amount of traffic for me which is delay tolerant, right? Or which we call deferable. Means it does not have to be delivered immediately. Okay, but the green line tells me the traffic which has to be delivered immediately, right? So I'm separating out, the application separates out its traffic into these two categories. And if that is known to the network, then the network can provision based on such explicit signals and can be much more efficient in the way that it does the network provisioning. And by more efficient, I mean it will provision less capacity. If it provisions less capacity, then we save money. And the utilization is driven up. It's just an efficiency argument. So now I'm going to be talking about how we do this optimization, and we call this whole thing the provisioning plane as opposed to control plane, data plane, management plane in networks. Okay, so let me describe a little about demand differentiation. So like I said on the previous slide, there are immediate demands and there are deferable demands. Immediate demands are usually because of user-facing needs. So take, for instance, your email application. When you click on a new message that is coming, you need to see that email immediately as you click on that, right? So when you click on that email notification, there is network traffic generated within the cloud that is hosting your email servers. That contributes to immediate or user-facing demands. But this email application will have lots of deferable demands, okay? Let me actually talk about what the deferable demands are first and then talk through this table. Deferable demands are where you don't have to immediately deliver some network traffic. So examples of this are load balancing. So in the email server example that I gave you, your mailbox sits on some server. Now, if that server becomes very hot or its CPU utilization becomes too high, the load balancing component will actually move your mailbox to a different server. Now, this is typically a background activity and starts before the server becomes absolutely unmanageably hot. Okay, so that means you have some budget of time before you can complete the load balancing. So delay tolerant or deferable is what we call it. Periodic tasks can be some analytics tasks which happen every day or every week. Server hydration is where a new set of servers suddenly gets commissioned in a data center. New hardware has come into the data center. Now you need to populate these servers with relevant data so that they can be part of the service. Again, this can be a slow process. Of course, does not take too much time, but it can take some time. And then finally, there's database geo-replication. So databases are typically replicated at least in one site, which is far geographically because for fault tolerance and reliability. So that creates a huge amount of background traffic. So again, that doesn't have to be delivered immediately. Okay, so this is about immediate and deferrable traffic. Now, yes.
You have a question. It's on the chat.
Okay, let's see. What are the optimization metrics for the network provisioning problem? Latency, throughput, average worst case, network costs. Yeah. So, right. So here we are looking at the efficiency problem while not compromising on latency, throughput, QoS, etc. Okay, so that will become hopefully clearer. But think of this as a constraint solving problem where the optimization is on the efficiency aspect, which is directly related to cost, while keeping constraints that latency, throughput, quality of service should remain the same as in the vanilla or the state of the art case. I hope I answered that question, but please hold on to that thought, and if it's not clear by the end of my
no, it's thanks. Yeah, I got it.
okay, great. So the way that we express immediate demands or user-facing demands is a standard way of expressing. It's a time series. So for a given 5-minute window or a half an hour window, etc., from data center Singapore to data center Hong Kong, the email application requires 3000 Gbps with an availability of 3 nines. That's what the first row here says. Now, I won't be talking about availability in this. So let's assume in this talk for lack of time. So I'm going to keep that on the back burner. We can talk about that if we have time later on. Now, deferrable demands on the other hand are a little more difficult to express, and this is where we bring in some new ideas. We don't express rate for deferrable demands. We express volume. So look at the first row in the second table I've flashed here. It says again, on 1st January at 12 o'clock from Singapore to Hong Kong, the load balancing application requires to send 1500 terabits of data within the next 7 days, right? So this is a slightly different way of expressing the demand than rate. And we will see how this can be used. Now, so the rest of my talk will focus on optimizing the provisioning plane, where we take this demand differentiation and reduce the amount of network capacity provisioned, right? Therefore, decreasing cost. There are 2 ways we do this, okay? The first is where we do this time shifting of deferrable traffic to calculate a smoothed peak. And the second is informed redundancy provisioning. So I'll talk about these 2 techniques now. The first, like I said, is time shifting. Okay, let's look at this squiggly graph, which is essentially a time series. Time on the x-axis, time in terms of days or weeks, and on the y-axis is the bandwidth used by an application. Let's say this is load balancing, right? Now, state-of-the-art techniques will take this graph. They'll draw peak. Typically they draw 95th percentile over, say, over a 1 month period, and they'll say this is the peak used in this last 1 month, and so we should consider that when we do our forecasting. What we say is that you don't need the peak. You need something lower than the peak. And why? How do we figure this out? Retrospectively, we look at the usage by the load balancing application, and we say had this path had less capacity, that is this red line, we would have been fine, because the traffic that is above the red line on the left side could have actually filled in valleys a little later, right? As long as that is within the deadline of 7 days, and we would have been fine. So you don't need to look at the actual peak of the traffic we sent. You do this analysis and you figure out you could have actually used this lower red line in our forecasting. So what this implies is that instead of using peak of usage forecast, which is shown by the black line in this graph here, if you look at the x-axis, this is for a 1-year period now. I'm taking every month and plotting a point for each month and then projecting it out. So instead of using the black line, I can use this red line to do my forecasting, and that reduces how much capacity I will need on every link. So this is the first technique we use, right? The second technique we use is called informed redundancy provisioning. So let me explain what that is. Every network will provision redundant capacity to ensure that if a network link goes down, you have enough on alternate paths to deliver the traffic. So in this example, we have data center 1 connected to data center 2 through 3 links. So that if this one link goes down, or even if 2 links goes down, you have redundancy to send your traffic. Now, what do we do with informed redundancy? We have one fat link to send all of our immediate and deferrable traffic, but we put in this three paths, or we put in capacity on these 3 links only for the immediate demands. Okay, so that's why you see that the 2 added links are thinner now than the fat link in the middle. What we say is that if this middle link goes, what we say is that if the middle link goes down, right, you can tell the load balancing or the deferrable application that pause your traffic, because this link has gone down. I know that this load balancing application, for instance, let's say it had a deadline of 15 days. 15 days is much longer than the time to recover of this link. Let's say the time to recover of this link is 2 days. So because this load balancing application has a deadline of 15 days, I'll tell it to pause, wait for this link to come up, then signal to the application that please feel free to send your traffic now. So I don't need to put in redundancy for these deferable demands. But notice that this is only the case when my mean time to recovery, or the time to recovery for this link, is much lower than the deadline for this deferable traffic. Okay, so doing this, we save on how much redundant bandwidth we provision in the network. Okay, so deferable demands can be paused for a substantial period, and this could potentially avoid provisioning redundancy for these deferable demands if that inequation I showed earlier holds. Okay, so putting all of this together, right, is so I've spoken to you about network provisioning. One very important piece of the network provisioning puzzle is this failure simulator. But yeah, before I talk about so there are 2 types of failure simulations that we do. One is point-in-time failures, and this is what people use in current techniques, right? They will just simulate one link going down or 2 links simultaneously going down. There is no notion of time in this failure simulation model, right? And then they'll say, okay, now we still have to deliver all this traffic and put in some redundant capacity. But since we are doing volume-based provisioning for deferable demands, we will now need time series-based failure models. Because, I spoke about this. So we'll need time series-based failure models. Because now we are talking about volumes of traffic to be sent, not rates. We are talking about deadlines, etc. So for every link, we'll have to generate or simulate failures across some given amount of time or a time window. This is needed for volume-based provisioning. So let me talk about the whole flow of the provisioning right now. So first thing we do is rate-based provisioning of the immediate demands. So for this, we take the immediate demands as input, do the forecasting and all that. Then we simulate point-in-time failures for this. And then after that, we get some amount of capacity provision, but this is just for the immediate demands. Then we do the volume-based provisioning of deferable demands. So for this again, we take the deferable demands, we simulate time series based failure scenarios, like and I'll talk about that in the next slide. And then the final output of this is the addition of this provision capacity for immediate demands and then the provision capacity for the deferable demands. So this is the flow. Now let me tell you how we built this time series link failures, because when we were working on this problem, we looked far and wide for something that does this kind of time series based failure modeling, but we didn't find anything. So we had to build our own way of doing this. So we have historical characteristics of link failures about a year or 2 years or something within Microsoft's network. So we take that and then we cluster similar links that have failed at similar times together. So in this example, link 1, 2, and 3 have been clustered together. And then link 4 is in a separate cluster. We use agglomerative clustering to do this. For every cluster, we generate a characteristic MTTR, or mean time to recover, and a characteristic mean time between failures, or MTBF. And then using that information, we generate a time series for every link on failures, right? It's a time series for, say, a 15-day window or something like that. So we generate these failure scenarios. We feed this into a constraint solver based model that does our provisioning. Okay. So now, yeah.
You have a question now.
Okay, I'll take a look. Are link failures related? It seems they are, yeah. So link failures can definitely be related, right? Which is why we are doing this clustering. If links were independent of each other and failing randomly, we wouldn't need to do this, and we would consider every link separately. We would build a model for every link separately and generate failure scenarios for every link separately as well. But we don't do that because we noticed correlated failures between links. And this could happen for multiple reasons. For instance, a fiber, a conduit that goes across the Pacific, let's say, right? It contains lots of fibers, and this could contain lots of links which we are currently using. But when a ship goes across and let's say it cuts this fiber, it's cutting a bunch of links all at the same time. So these kinds of failures cause correlations between link failures. We don't have the ground truth on all of these, on the physical connectivity of these links. We tried to get it, but it's difficult to get. So instead we use this data driven approach, and we try to be as conservative as we can. Yeah, excuse me. Does that answer the question? Yeah, okay, thanks Mupulika.
So there are a couple more questions out there on the chat.
Okay.
Oh, there's one more question from Kavansh.
So the question reads, in my understanding, load balancing is used in high availability scenarios. Can you provide a few examples on which kind of load balanced applications can defer their demand? Yeah, so I gave you a brief description of this early on. Let me talk in a little more detail, right? So our email server is called Exchange. Now Exchange works on top of a data engine, which is used by multiple applications and services within Microsoft. This data engine supports a form of load balancing where it will look at the usage, compute and storage usage on every machine. Now, if it finds this is above a certain threshold, and this threshold is determined by again observing the usage on these machines and saying that maybe in 1 month, or in 3 months, this server, if it continues the way that it's going right now, it will be unusable because it will be just too full of data, too much storage, too much compute is being used. But that will happen if we just don't do anything about this for the next 3 months or so. And I'm using these numbers loosely. Then you can say, okay, to avoid this situation 3 months from now, I'm going to move a bunch of mailboxes which this server hosts to another cooler server, which is not as much used. So speaking loosely, then this means I have 3 months to move these mailboxes from this machine to the cooler machine, right? And we are being conservative when we say that, okay, I have only 15 days or 7 days to do this. We're just being careful. Does that answer the question? I hope so. Otherwise, feel free to ask another question. So load balancing is one example. And I also spoke about server hydration, analytics tasks. I don't know if people use that. There might be a few people here from companies who might get an every morning a to-do list, or something that says you haven't responded to this person's email. All those analytics, they can run, they have a window of time to run, like 12 hours or 24 hours. So you have that window of time to deliver traffic related to that application. So these are some of the examples. Yeah. Okay. Okay, let me just move on. Yes, so this was actually good that you asked questions there, because now I'm going to be talking about the evaluation and show how much capacity savings we get using a proof, which is our constraint solver based provisioning mechanism. And the first graph I'm showing is for the load balancing application with for the Asia Pacific region. So you see these two bars. The first bar on the left is just using the time shifting approach, which I talked about first. The second bar is for time shifting plus the informed redundancy provisioning. Y-axis tells you how much capacity we've saved. Of course, I can't tell you absolute numbers, so everything is going to be in terms of percentage savings. So with time shifting only in the Asia Pacific region, I get 20% savings, which is quite significant. And when I throw in informed redundancy provision, I get an extra 10%. So a total of about 35% savings is what we get in the Asia Pacific region. The second graph here shows the same numbers for the North America region. With time shifting only, we got about 7% savings. But when we threw informed redundancy provisioning, this increased quite dramatically to about 25%. And the reason for this, why informed redundancy provisioning works so much better in North America, whereas it doesn't save us that much in Asia Pacific, is captured in this graph on the right. The graph on the right shows you on the x-axis time to recover for link failures. For every link or for the set of links in North America, which is the dark blue line, what is the time to recover? And what is the time to recover for Asia Pacific is shown by the light blue line. And this is a CDF. So what these two lines are telling you is that in general, if a link fails in Asia Pacific, it takes much longer to recover than in North America. All right. And one question is why this might be. And the reason why this is because if you look at the Asia Pacific region, you have a number of countries which are linked by undersea cables. Whereas if you look at North America region, it's mostly land cables. Land cables are much easier to repair if there's a cut. Whereas undersea cables sometimes take 6 months or even more to repair, right? So now when you have time to recover which is very low, informed redundancy comes into play much more, because now you have links that are recovering within 1 day, so you don't need to put in redundancy for applications that have deadlines of 7 days or more, right? Whereas with Asia Pacific, if you have links failing for 6 months, you need to put in redundancy even for the deferrable applications. So that's why we don't save as much with informed redundancy provisioning in Asia Pacific, but we save a lot in North America.
A quick question out here.
Yeah.
The question is like saving over what time period?
Could you repeat that? It was a little unclear.
It's saving over what time period is the question out here.
Yeah, so I think we ran this for 1 month of data. Yeah. Okay. But it will translate to 3 months, 6 months, forever as we go on. Okay, so the blue bars were for load balancing. The orange bars are for the server hydration application. So just to remind you what server hydration is, new compute servers land in some data centers, and then you have to hydrate them with data relevant to the application. So in the email server example that I tell you, you have to move mailboxes from some old servers to these new servers, which again uses wide area network bandwidth when you're moving it across data centers. So is very data hungry, but then it can happen in the background. It can happen over 3 months or so. So you have 3 months to move all this data and then get these servers into the service. So that again ends up saving us quite a bit when we add server hydration. So again, we saw a lot of savings in APAC because for the region that we simulated, the APAC region saw lots of hardware, new hardware come in. The North America region didn't. But if the North America region actually did, you would see very similar savings. The final graph I want to show for this part of the talk is on the availability aspect. So I didn't speak about availability, but our algorithms have a way of ensuring this 3 nines or 2 nines of availability, etc. Now, the point here I'm trying to make is that you can design or you can specify your requirements by looking at this curve. So the x-axis is deadline and y-axis is the capacity that is provisioned. So what this is saying is that if you look at the 2 points I have outlined in black, it's saying that when you have traffic with a deadline of 2 days, but you want 3 nines of availability, the capacity provisioned is the same if you had traffic which has a deadline of say about 1 day. I'm approximating here, a deadline of 1 day, which is lower, but with only 2 nines of availability. So by looking at these curves, you can decide, you can make an informed decision on how you can relax deadline or availability requirements so that the capacity provisioned is the same. So I'll conclude this part of my talk by saying that cooperation between applications in the network allows for these kinds of rich optimizations. And I spoke to you about optimizing the network provisioning plane through our scheme called Approve, which uses two main ideas. The first is this retrospective time shifting, and the second is informed redundancy provisioning. And over all applications, we see a capacity savings of about 30 to 40% in the North America and Asia Pacific regions, respectively. So yes, so this is the end of the first part of my talk. I have only 15 minutes, so I will summarize the second part. But before that, I want to make sure I answer all questions about this part.
There's a question on the chat. Mukulika, you might want to unmute and ask the question.
Yeah, sure, Mukulika. Just ask. I can't hear you clearly. Is it just me or?
No, I can't hear Mukulika. You might want to talk louder.
Or come closer to your mic.
Am I audible?
Yes, much better.
Okay. So the question is that I could not understand where is this bandwidth saving coming from. The reason being the entire motivation of provisioning is that when the link failure is happening, you are stopping it for the timing, but that does not mean that the data is not going maybe after 2 days when the link is up.
Correct, correct.
So then why is bandwidth being saved? Like it will be utilized not today, but maybe after 2 days.
You're right. But what we are saving on is the amount of redundancy we are putting in the network. So let me go back to that slide, which explains that. Yeah, this one here, right? So if you look at, if you look at the graph on the left, right?
Yes.
You put in 3 times the amount of capacity you need, really, just to take care of the situation where both these two links, any two links go down, then you will still have enough bandwidth to send, enough capacity to send your traffic. That Mukulika is clear, right?
Yes. Now I understand.
So on the right side, we are just not putting in that redundant capacity for the deferrable demand. So remember that we were differentiating between bandwidth used and capacity provision.
Okay.
So yeah, so the capacity provision goes down.
So
The
in that sense, one would expect more savings, right? You are essentially lowering the capacity a lot to
yeah,
make sure that you can save the bandwidth when needed.
yes. But are you saying that we should save much more than what we should,
Yes,
or?
yes, yes. That's what I expected to, because now you are not over provisioning and so on.
Well, we are saving about 35 to 40%, which is quite
Okay,
significant.
okay, okay. Thank
Yeah,
you.
yeah. But and I would say I thought the other way around. I didn't think we would save quite so much. But if you look at traffic, right? In general, if you look at the characteristics of traffic in these used in these cloud vans, user-facing traffic has extremely high latency requirements or extremely low latency requirements, but the background traffic is the bulk of traffic. So copy traffic, replication, server hydration, all these can tolerate, they are deferable and delay tolerant, but they are huge, huge amounts of volumes of traffic. And that's why we get savings by using this approach.
Okay.
Any other questions? Okay. So then I have about 10 minutes. So I'll quickly talk about the next piece of work we've done in this space. This is slightly different, right? This is not to do with networking specifically, but it's a broader problem. And the problem is of any data science applied to systems, right? When you are doing this holistic kind of data driven analytics, you need data from multiple subsystems. So you need data from the user level, application level, infrastructure level. But any one data scientist does not have access to all of this data, and they don't even know if the data exists or not. So we faced this when we did this whole approve project, right? Because we needed data from the email server, exchange server application, from multiple components within that application, the user facing components, the deferable components. We needed data from the network, Azure network team, right? So we ended up spending a huge amount of time talking to people who generate this data and understanding where the data sits, if it even exists or not, and so on. So we said, this is just too much work. Let's try and build an automated data discovery engine. So that's how we came up with Data Lake Navigator, which discovers related data at scale. And I will show you how we are using our CrossLayer advantage even in building the Data Lake Navigator. So again, let me motivate this with an example. Let's say a developer or a data scientist is trying to build a root cause analysis dashboard. So essentially, there are alerts that come in, and they want to figure out what is the root cause of this alert. So they start with a table that stores these alerts. Now, the cause for these alerts could be multiple. Maybe the network failed, or the system itself failed, or the application had some problems. So, you have to take this alerts data and associate it with data from the network system or the application. So, here are 3 example tables. Now, if you stare at these tables carefully enough, or these green columns, right, you will see that they are related. So the machine column in the alerts table is related to the server column in the EDS table, the second table on the right. It's also related to the host column in the application table. Also it's related to the data center table in the IP fix table, because the machine itself is associated with a certain data center. So to find these relationships, we need to know these relationships to associate all this data together or join them. But there is no global schema, because each of these tables are maintained organizationally in different parts of the company. There is no global schema that you can refer to, unlike traditional databases. As a result, it can take months to discover all this data for your specific problem, which in this case is building a root cause analysis dashboard. So the state of the art to address this problem is to build what people call a data relevance graph. So each node in the data relevance graph is a column of a table, and there's an edge connecting two columns with some form of a relevance metric saying that these two nodes are connected with a particular weight, which is the relevance metric. So the relevance metric used in techniques that people have proposed in ICD and SIGMOD in recent years is the Jaccard coefficient, where the Jaccard coefficient is a well-known technique where if there's more overlap between two columns values, then they're considered more related. Then there are metadata based metrics as well, where you look at the column name similarity. So if two columns are named server, then you say they're related. So these are some techniques that state-of-the-art techniques use, state-of-the-art algorithms or systems use to relate data. But the current techniques, they just calculate these and they leave it to the data scientists to figure out whether the value of these metrics means these things are related or not. So for instance, if I say Jaccard coefficient is 0.7, does that mean that the two columns are related? It's unclear, right? So they leave it to the data scientists to decide. So that's a problem. And the other problem is that they don't scale well because they scan entire columns. So here's where we leverage the CrossLayer advantage that we have at Microsoft. We have access to logs of millions of daily jobs that have run for over a decade on our data lake, which is called Cosmos. So we have all these queries that have run in our data lake. Now, the second observation that we have is that these scripts, which are written in a language called Scope, which looks just like SQL really for all practical purposes, these scripts have join clauses, which we can leverage as ground truth. So what is a join clause, right? So if you squint at this piece of SQL that I have on the right, the join clause is here, and it's telling me that the server column in the store ops table is related to the machine name column in the machines table, right? And in some sense, it's telling me these two are related. And so we can leverage this collective knowledge that developers have captured in writing all these queries over the last decade to figure out what columns and what tables are related. So this is what we do. So we take all of this, we mine all these join clauses, and we build a machine learning classifier. So I don't have time to go into all the details, but I just wanted to make the point that we are using all these queries that we have access to as ground truth and using that to build a data relevance graph, which will tell me that two columns are related or not, as opposed to just calculating some metrics and labeling the edges with those metrics. Let me just skip all these slides. Right, so I'll just talk about how well our techniques work. Let me skip this because I haven't talked about this. Our techniques scale very, very well because we have this ground truth, right? So we use that, and instead of traditional techniques, we took 30 times faster amount of time to build the data relevance graph for a large subset of our data lake. And the next thing we did was to determine if this data graph is actually accurate. So we manually labeled data set using domain knowledge, and we found that our graph, right, gave an F1 score of 0.79, whereas previous techniques gave much lower F1 scores, which showed that using this ground truth actually helped in building more accurate data relevance graphs. So with that, I will end my presentation. And I will also put in a plug for a third piece that we have recently been working on. This is about using reinforcement learning to tune clusters. This is right at the bottom of your screen. It's a system that we call SelfTune. and this is going to appear at NSDI 2023 on how you can use reinforcement learning to tune and improve cluster managers for better throughput, latency, etc. So with that, I'll end my talk, and if there are any other questions, I'm happy to take them.
Thank you, Dr. Ranjita. So anyone in the audience, if you have a question, please raise your hand, or I'll unmute and you can ask your question.
Ranjita, I wanted to ask one more question. That I thought that sometimes you don't have transparency into what a VM application is trying to do for IP related issues or privacy related issues, and as the VM manager or the cloud provider, you actually don't know what are the latencies or the deadlines which are needed. So is it like the SLOs are now modified to provide you this extra information to look into things, or they are also, as you say, Microsoft background traffic is anyway much more than what these individual VMs are doing?
Yeah, so I think you brought up 2 points, 2 great points in your question. The first is Microsoft versus third party, right? So when we run third party applications, we don't have access to any information about their deadlines, etc.
Right.
We can't assume anything. So this is why we are concentrating on Microsoft applications such as Exchange, Teams,
Okay.
etc.
Hmm.
Right? So now the second part of the problem is, even if you are working with a Microsoft application, which is a first party application, are you really, how do you know the deadline? It's not easy. So we had to go and interview the domain experts with the engineers who put different components within the Exchange server to determine what is the suitable deadline. So there was a lot of back and forth involved there, because sometimes people haven't even thought through what a right deadline value should be for this. Yeah.
And the abstractions also, is it like there are many teams and many applications in Microsoft? So if as an application developer they want to talk to a systems person like you, the abstraction might be not clean enough, right? So you might say that these are 4 metrics to optimize, these are the knobs that you can change. So is it like you are also building this kind of an abstraction so that any Microsoft developer working on the Teams application, for example, so they can talk to your thing, or is it currently just one blob, and for every application you are tuning it separately based on what it needs?
Yeah. So our approach is actually right now the latter, because if you look at usage of the WAN, you will see heavy tail distribution. So there will be probably 4 properties or 4 applications which use maybe around 70 to 80% of the WAN. So if we just talk to them and we convince them to use these techniques, then we've addressed about 80% or some large fraction of WAN usage.
Okay.
So that is the current mode of operation. So what you said second is what we're doing, which is manually talking to these people to provide this informed forecast to the network, instead of not providing this forecast at all.
Right.
Going forward, when we have really realized at least savings for these 3 or 4 applications, then if we are targeting the long tail, then we'd have to do what you're suggesting, which is provide these abstractions, allow people to automatically specify this in some machine readable way and so on.
Yeah, and you will enforce it at a lower end, how to handle those requests. Yeah.
Yes. But we're not doing that right now. Yeah.
Okay.
Is there something on chat, or no? It's just a thank.
Yeah, it's a thank you note.
Yeah, you're welcome. Okay, I think I'm done, unless there are any other questions.
Yeah, if there are no other questions, I'd like to thank Dr. Ranjita on behalf of iMobile, and it was a very informative session. Thank you, and I'll just pass over the mic to Shundip to add in the final. Thank you.
Yeah, thanks Ranjita for the interesting talk, and thanks Ogata for coordinating the session. And finally, thank to all the participants for attending this talk. Hopefully, we'll be able to have you in the next talk as well.
Yeah, thanks for having me.
Thank you.
Thank
Bye.
you.
Okay, bye.